So, very first thing you'll notice, for those of you that actually printed out the lecture slides, this slide isn't in that packet. That's because I recommended that a slide like this get added to it, and they decided that they didn't think it was important enough to add, so it didn't make it in. I still think it's important, so we're going to talk about it. Okay? And it's pretty much a summary of what we talked about last week. Okay? So it's the relationship between bonds and forces. They are still two distinct things. Okay? So don't start cross-pollinating them, I guess. With the bonds, you've got those three forces: ionic, polar covalent, and covalent. Okay? One of the nice things about this color wheel, or the colors associated with it, is let's say you have a covalent bond, and for sake of argument, let's call it a purple covalent bond. Okay? What does that mean about the strongest force that that purple covalent bond could generate? It's going to be a purple London dispersion force. Okay? So it translates fairly cleanly straight across. So if you have a green polar covalent bond, you're going to end up with a green force. Okay? It's a gradient all the way across. If you've got some kind of blue bond, so somewhere in between polar covalent and covalent, so low differences in electronegativity, that's going to generate, that's going to generate a weak, come on now, a weak force. Okay? Somewhere in that London dispersion to dipole range. Okay, so that's the intent behind it on how you're supposed to be interpreting it. Again, remember, they are two separate things. Okay? We can use this information to our benefit for almost anything we'll do in lab, and believe it or not, 90% of the chemistry that you'll see in lecture is also explained by these bonds and forces. Okay? And depending on who you have, if you have Gould, it goes into a whole lot more detail with quantum chemistry than you'll see in most places, and in which case this is way too simple for him. Okay? So let's take advantage of this information to see what would happen with TLC. Okay? So we can take a look at our RF values. Let's say I want to know the lowest RF value of those two. Okay? Well, what does lowest RF mean? Whoops. Let me try that again. Lowest RF means most polar. Okay, well, what is most polar going to mean? Okay, the strongest forces you can get. So you're going to start pushing up towards ionic bonds. Okay, so the very first thing we could do is say, okay, well, ionic bonds are going to be the important force. So what kind of bonds would I expect to see for an ionic bonding force? Translates across to ionic kind. Okay? So we can now look at our two compounds, water and CH4. Do either of them have ionic bonds? No. So let's drop to the next most polar force. What's the next most polar force? Hydrogen bonding. How do we get hydrogen bonding? We can go across the other side. We need polar covalent bonds. Okay? So we can now look back at our two structures and identify what types of bonds are present in them. What type of bond, mind you, is present in water? Okay, a lot of people might say hydrogen bonding, but is that a good answer? Hydrogen bonding is not a bond, it's a force. What's the bond? It's polar covalent, which is what we were looking for. We were looking for a strong polar bond, so that sounds like a likely candidate for being a most polar compound. We'll still have to compare it back to the methane. What are the bonds in methane? Carbon to hydrogen, which gives us covalent bonds. Well, that's weaker than polar covalent. So we're looking at water being our most polar compound, which is going to generate the lowest RF. Okay? So it's a question of stepwise interpreting each of these things and trying to build upon that information. Okay? There are lots of physical properties that are determined based on the intermolecular forces: melting point, boiling point, solubility, which we're going to look at today, reactivity, can also be predicted based on these intermolecular forces, looking for those partial charges. Okay? More relevant for the lab, all sorts of techniques fall out of this. TLC, extraction, chromatography, recrystallization, synthesis. Okay? Conveniently enough, each of those little experiments that I've mentioned there are the next sequence of experiments. You already did TLC. This lab, you're going to be dealing with extraction and column chromatography. The following lab is a recrystallization. The following lab is a synthesis. All of them, I'm going to be beating you over the head with this same figure, asking you to apply it to that situation. Okay? That's how important these things are. Go ahead and move on to the next one, but I'm going to address solubility. I'm hoping for a nice white sheet of paper. Didn't quite give it to me. So we'll talk about it slightly differently. So we can take now a look at what's going to happen for today's experiment, or the experiment this week. Everybody complains that organic chemistry has no application. Oh, it's irrelevant, it's esoteric, nobody likes it. Okay? I don't care if you don't like it. It does have plenty of applications. Okay? Most of the cancer drugs out there have been sourced and found where? From plant life, or even some weird sponges, which you could say, or animal life. Okay? So we are taking advantage of nature to make drugs for us. Unfortunately, those drugs don't get made in a very large amount, okay? So we have to be able to synthesize them. So our very first step is to find out first if it is a valid drug. So we've got to get the drug out of the plant. Okay? Once we've got it out of the plant, we then need to isolate it. Then we need to figure out its structure so that we can then attempt to make it. Okay? So that's our goal when dealing with a lot of organic chemistry or natural product chemistry. Well, spinach in this case doesn't produce only things to make Popeye strong. It's got a bunch of other things involved in it, right? We don't want those other things, so we've got to come up with some way to get rid of them. Okay? What's the easiest way to get rid of them? The thing that we should be relying on to figure out how to get rid of them? Rhymes with horses. Intermolecular forces. Okay? So what we'll do is go back to the structures and see if we can figure out some information about them so we can figure out some way to separate them away from each other. So we can take a look at 4 representative compounds that could be potentially found in spinach. Okay? Could we go through and decide which of those might be the most polar? If I could, I mean, go ahead and do that. Which of those might be the most polar compound? Your eyes should probably drift lower and lower on the screen, okay? And not because you're falling asleep. Ah. Okay, never mind then. Which is the most polar? Probably the one on the bottom. That's where I'm telling you to go. Why is that one the most polar? I see a charge. What does the charge mean? I have an ionic bonding. Okay, which is an extremely polar force. So that compound is likely going to be the most polar compound. But wait, you all say.
There's also...
But wait, there we go, I heard it. There's also... If we go up and look at that top one, what did I just circle in now? More charge. Why is that charge not as polar as the bottom charge? Where's that charge located? It's located surrounded by a whole bunch of nonpolar things. Okay? Whereas in the case down below, we've got that same charge, but it's now accessible. Okay? It's floating out in the middle of the solution. Okay? So what we can do is now try and take advantage of these intermolecular forces and try and bulk separate them away from each other. Those of you in biology, tell me what that bottom structure is. What does that look an awful lot like? A phospholipid. Where do we find phospholipids? Cell membranes, okay? Like the cell walls of the spinach plant. We don't want that. We want the things on the inside, okay? So we've got to come up with some way that we can try and bulk remove some of that material. One way would be to grind it all up, pulverize it, so we break all the cell walls open. We're still going to have solid parts, so we can filter out the solid parts. And now we've got kind of a solution that has some organic components and some non-organic. Okay? What might we expect to see? Okay, let's see if this slide is going to do it for me. Not going to do it for me. So let's go through and take a look at this. That first part lists out all those structures that I just drew up for you. Okay? We now want to be able to separate some of those organic things away from the inorganic things. Okay? Most inorganic compounds are, what's your question? Huh? Okay, what's that? Okay, we could try and centrifuge it, and that would separate based on density. That gets rid of some of it. But if it's soluble, okay, that's not going to remove it necessarily. It's only going to separate between the individual densities. Okay, and we'd have to get really high-powered centrifuges to really do anything helpful for us there. Okay, so what we're going to do is rely on another property. We're going to rely on the solubility of those individual components. Okay, our organic pigments, or the things that we're in this lab are targeting, happen to be very nonpolar. Okay, well, if they're nonpolar, would we expect them to be soluble in a very polar solvent? No. Why would they not be soluble? Okay, like dissolves like. So if we take a look at, dang, you, stop that. Okay, let's take a look at, come on, give it to me. CH4 again, and water. We've got those two structures now. If we were going to look at solubility, we'd be asking, are those two compounds going to mix with each other? What do you think? Should they mix? No. Why not? They have different intermolecular forces. Well, why is that important? Well, what we can do is now change our focus and look at what's happening with water. Okay? If we draw on another molecule of water, we can show a very interesting intermolecular force. What the hell did you just do? Okay. Oh, and it just erased everything. Okay, well, we'll just pretend. Between those two water molecules, what intermolecular force do I have? Hydrogen bonding, which is a very strong intermolecular force. If I now look at the interaction between water and methane, what type of interaction do I have there? London dispersion. Is that a strong intermolecular force? No. Why is it not strong? We don't have anything to cancel out the partial charges within the water molecule. Okay? So what ends up happening is we lose stability by mixing them. We tend to always transition towards things being more stable so they don't mix. So we're going to do that same general idea with the individual pigments and components within our spinach extract. So we'll take the organic compounds, which are very nonpolar. Those will interact with a very nonpolar solvent. Okay? And we'll take our very polar components, and those would interact with very polar solvents such as water. This technique is referred to as liquid-liquid extraction. It's a bulk separation technique designed to remove as much as we can as quickly as possible. Okay? So if we go through and do that, what we might end up seeing, after we get through all these silly animations, is something along these lines. Okay, we get this huge green layer on top, and we get this nasty yellow-looking layer on the bottom. Okay? Why would it be green on top? Why would it be green in general? Because spinach is green. Okay? So most of the compounds that generate the green color from spinach happen to be organic. So they're going to sit in the organic layer. And our aqueous layer is going to contain all that other stuff. Okay? So we get two layers. Which layer should be on top? Exactly the right answer. Comes back to density. It has nothing to do with organic versus aqueous. It only has everything to do with just density. So whichever one's less dense is going to be on top. Whichever one's the most dense is going to be on the bottom. Okay? When we're dealing with most things organic chemistry, so in the case of your experiment, the organic layer is hexane and acetone. And our aqueous layer will be, of course, based on water. Hexane and acetone happen to have a lower density than water, and so they float on top. Okay, so it all comes back again to that density. So now we've got a green layer that has a whole bunch of organic pigments within it. Okay? We now need to separate those different pigments away from each other. How could we separate different organic compounds away from each other? Did you say learn any new techniques that might allow you to separate those? TLC, there you go. Go figure. Okay? The last lab that you guys did separated organic compounds away from each other based on their intermolecular forces. Okay? We're also going to take advantage of that in this lab. Except what's one of the primary drawbacks for TLC?
No
We can only use a very, very small amount. You guys use those microcapillaries, or at least that's what you should have used to spot your TLC plates. Those release pretty much a drop of liquid. By a drop, we're looking at 1 microliter. Okay, if we take a look at this figure, how much liquid do you think is in that layer? A lot. It's a heck of a lot more than 1 microliter. Okay? So we're trying to separate a lot of compounds. If we were going to do TLC, how many TLC plates would we have to use? A lot. So all of you working together, the entire organic contingent of students, okay, all of you running 5 or 6 TLC plates could potentially separate all of that. Okay? You could then collect it all and then sell it off as some fancy drug. Okay? That's going to be a lot of effort, a lot of time, a lot of work. Okay? It's just not going to work out very well. So what we end up doing is coming up with a new technique. That new technique applies the same technology, if you will, as TLC, the same general principles, except all we do is turn it on its head. So we just flip it over. So we'll take our TLC plate. Okay, you notice those were kind of flexible. What we'll do in theory is turn it into a cylinder. So wrap it up so it's a nice little cone. Or not a cone, but a cylinder. Okay? And then what we'll do is instead of letting the solvent run up through it, we're going to turn it upside down. We'll let the solvent run down through it. And that's going to be our separation. So if we looked at TLC, and I use my thumb and finger here as an example, my thumb would be which compound on a TLC? What could you tell me about the thumb versus my index finger or my pinky? It's going to be the least polar compound. If I now go through and look at column chromatography, what do I need to do? I take my TLC plate, turn it into a cylinder, which I can't really do with my hand, and then turn it upside down. Which compound comes off the column first? The least polar compound. Okay? The one with the highest RF. Okay? So this technique is our column chromatography. Okay? It's one of the most commonly used techniques in research labs because it allows for 2 big things. Bulk separation. So if we do it very quick and very dirty, we can get kind of bulk separation, remove a whole bunch of compounds fairly quickly, and do a whole lot of that compound. Or we could take it a little bit longer to run that process, and we can do an actual purification. So purification is the same thing as separation. It's just a little bit more refined. Okay? And it's, again, the same principle as TLC. All we've done is taken our TLC plate and turned it upside down. Okay? So we're still looking at the differentiation between intermolecular forces. The stationary phase in TLC, was what? Silica gel. What's the stationary phase going to be in column chromatography? Still silica gel. Okay? Our mobile phase in TLC was? No, that was the compound you were separating. What caused the compounds to move? Some mixture of liquids, bulk-wise known as a solvent. Okay, so our mobile phase was just some kind of solvent. Same thing's going to apply in column chromatography. We've got our stationary phase as our silica gel, and then we've got our solvent, which will act as our mobile phase and help with the separation. Okay? Column chromatography, depending on what scale you're dealing with, will come with different features. So if we look at the macro scale, it's really nice because right at the bottom of that little dealio, what do we have? Anybody recognize what that image looks like? It's not quite a stopcock, but pretty close. It's a valve. We can control the flow of the liquid running out of that. That's really nice. So we could set up and say, oh, I don't want to be running my column quite yet, so I'll close it. Okay? And when I want it to run, I can open it up. So that means I can control when I've got a container underneath it or when I don't, so I can do everything nice and neat. Unfortunately, you guys don't get to do the macro scale. You guys get to do the micro scale. Anybody notice anything interesting about the bottom of that microscale column? There's no valve, which means when you are ready to, or when you think you're ready to do the column, you better have everything handy and ready to go because you cannot stop your column. Once it's started, you have to finish it. Go all the way through the entire process. So make sure you've got plenty of containers to collect. Okay? So, okay, fine, leave it blank. Talked about our stationary phase. What about our compounds? Okay, so again, if we looked at TLC, pinky and thumb. Okay, thumb being up top for those of you listening on the slides that can't see my hand. Our thumb's up high and our pinky's down low. Which compound is the most polar in TLC? The pinky, the bottom one, because it's stuck. It's not traveling. If we now move to column chromatography and we turn it upside down, which compound comes off last? Okay. Where does the compound come out? Comes out at the bottom. Which compound comes off last?
The most polar.
The most polar, which is my pinky, which for some reason is tweaking out right now. Okay? The most polar compound is going to stick to the column, and it's going to take longer to come off the column. Okay? So it'll travel more slowly. Non-polar compounds, conversely, didn't stick to the TLC plate. They aren't going to stick within the column, and they're going to flow right off of that really, really fast. Okay? So if we now switch this around and look at a time-lapse photography of what's going on with this. We've got our TLC plate on the left, and then we've got our columns going on to our right. What can you tell me about compound B? It is the least polar because it has, what about its RF? It's the highest RF. Okay, so it's going to be our least polar. So if we now go back to our column and try and track down what's happening with that. Okay, we'll start off in that first figure. So what we've done is we added our column, or our silica gel, to our column. Okay, and then we put solvent in behind it first. So there's something actually in front of the first. Okay, we add solvent to it, and what's going to happen? Well, let's take it a step further back. Sorry. Silica. What phase is silica? Stationary, good call. Physical phase. It's a solid. It's a solid in TLC plate. It's a solid in the column chromatography. So if we add that solid powder to the top of the column, what's going to happen? What are we also incorporating at the same time? It's invisible. Gas, air. We're incorporating air naturally as we do this. So if we now put solvent in the top, what's that solvent going to do to the air? It's going to start to push it and cause it to shift around. Okay, as the air shifts around, what happens to the silica? It's also going to shift around. So if we now put our compound in behind it, our compound's now shifting around physically with the silica, not just interacting with the silica gel on its own through the intermolecular forces, which means we've created an inconsistency. Our whole goal is to make sure it's as consistent and smooth running as possible. Okay? If we've got air in there, it's not going to run smoothly. So our very first job is to make sure that that column is as consistent and even as possible. We're going to load it with as much solvent as we can so that it's all nice and wet, nice and evenly packed, hopefully no air inside it. Okay? We can then load our compound onto it. So we'll then put our solvent, or our small amount of solution that has our compound in it, onto the top of the column. What's going to happen to our compound now? Any ideas?
It's going to progress downward to the solution.
Okay, should it move? You're probably not going to move a whole lot. You do have gravity pushing down, okay? But gravity is not going to be strong enough to break the intermolecular attraction between the silica and your compound, regardless of how polar or nonpolar your solvent or your compound is. How do we get our compounds to actually move? You took TLC. What did you do with TLC? You spotted your compounds on it. That's exactly what we just did now. Then what did you do? You just kind of held it up in the air, turned it upside down, shook it a whole bunch? What capillary action? You had to take your TLC plate and put it in some solvent, so the solvent could rise up through it. How are we going to get our compounds to move down the column? You need to have solvent pushing along behind it. So once your compound's loaded onto your column, you can add solvent to the top. That is now going to push your compounds through the column. Okay? And it will push them according to their strength of interaction with the TLC plate. So if we take a look at our first case, we've just loaded it. And the second case, what's happened? All we've done is start pushing solvent through it. What would we be collecting at the bottom? What do you think's in that beaker right now? Solvent, right? What happens when we get to that third case? Where's compound B? Almost to the column, almost to the bottom of the column, almost to the point where we could get it out. Okay? So mostly what's in that third fraction right now is going to be solvent. What should I do in case B? Or not case B, that fourth case. What's special about that beaker more so than the first three? It definitely does contain compound B, that's true. There's something else that's special about that beaker. What was our goal in this experiment? Purify compounds, separate them away from each other. So we were trying to separate A from B. Okay? Did we add anything to do this? We added a solvent. So really, when we started this, we aren't separating just A from B. We're separating A from B from solvent. So we've got another compound in there, compound C. Our goal is to make sure they're as far away from each other as possible. What's special about beaker B, or that fourth beaker, our circled one, is that that's a new beaker. Why would we want a new beaker at that point from beakers 1, 2, or 3? We don't want to mix it with compound C. Okay? We're trying to limit its exposure to that other compound. There's no sense in us making it more impure by incorporating more solvent C.
So is it just water there?
That beaker is going to be compound B and the solvent that's still pushing it out. So it is still coming out contaminated, if you will, with your solvent. But it's not as much solvent if you just collected everything together. Okay? We're just trying to limit that exposure as best we can. Okay? Ideally, there would be another figure in here, sitting right in between these two. Okay? That figure would show compound B is all the way off the column. Okay? How can I get compound A to run off the column? I can continue to put more solvent down, right? As I put more solvent, that's going to continue to push. Okay? What's going to come out during this iteration, right in that space? More solvent, and just solvent. Okay? So I'll collect that separate from B. And then we get to that very last case, which I guess we'll call fifth. Okay? And now I'm going to collect again in a separate container, because I don't want to collect more of the solvent along with it. Okay? My goal is to try and get these in as many different containers as possible so we can easily identify and separate each of these things. Make sense? Okay. We just talked about polarity. We won't deal with that. What happens if we change the mobile phase? This figure is slightly odd, so let's go ahead and add on a little thing. Your mobile phase is these blue lines. So we put the same amount of solvent into each of these. Okay, what's different?
Did you change like the identity of the
The identity of the mobile phase has changed, but it's the same compound, same stationary phase.
Then will be a different force.
I'm pushing the compounds with a different amount of force. Okay? In one case, I've pushed the compounds really, really hard. How could I tell that? They moved really, really far. And in one case, I didn't push them very hard at all, which means they don't move. They stay right up at the top of the column. So which of these cases would be a hard push? Right or left? Right. Okay. What measures our effective pushing strength? Polarity. Okay. What happens if I have a more polar solvent? What am I doing? I'm breaking those strong intermolecular forces between the stationary phase and your compound. which means your compound no longer interacts with the stationary phase. If it's not on the stationary phase, what's it doing? It's moving down the column. So the one on the right would be our more polar solvent, and the one on the left would be our non-polar solvent. Okay, you can go ahead and start passing out the group activities. While she's doing that, we'll go ahead and answer these questions. We've got these three compounds, A, B, and C on TLC. What's the first thing that you should do to answer this question? I would go even further back than just trying to figure out most polar. The question asks you highest RF. What does highest RF mean? We're looking at the lowest polarity. What's lowest polarity mean? What type of bonds should we expect to see in our structure? Covalent. It's not quite how you spell covalent. Okay, so we can now go through and look at each of those individual structures and see what we see. Compound A. What intermolecular, what bonds do you see in compound A? We see some covalent bonds, but we also see polar covalent where? Good guess, the OH. Polar covalent, that's not a very low polarity. So let's go ahead and move on to compound B and see what B has. What does B have? Polar covalent again, but now there's two of them. Which one's more polar? Compound B. It has more polar interactions. And we move to compound C. All covalent bonds, which means lowest polarity, which means highest RF. Okay. Next question, which it didn't do. Now instead we've got something very similar, except now we're going to say column chromatography. And it asks which is the last fraction. What does last fraction mean? Last one to come out. Good answer. It's going to be the most polar. Most polar means what type of bond? Our strongest bond, or our most polar bond, which would be ionic. None of these are ionic, so we take the step down, which would be polar covalent. We already went through and did this. A and B both had polar covalent bonds. Okay, which one has more polar covalent bond? B. It's going to have more hydrogen bonding interactions. It is more polar. That one's going to have or come off the column last. Kind of makes sense? Okay, go ahead and answer the questions from that group activity. I am going to attempt to